Hello and welcome back to Probability Theory, the video course where we talk about random variables, statistics and related stuff. And in today's part 30, we will talk about the so-called strong law of large numbers. So you see, we continue our discussion of this important law, but in an extended formulation. However, before I tell you how this is different to the weak law of large numbers, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, you can use the link in the description to find additional material for all the videos. And with that in mind, I would say we can immediately start with the setup from the last videos. One possibility to describe that would be to say that we repeat a random experiment again and again. Hence, we get a whole family of random variables, which we could call x1, x2, and so on. And then what we get is that they are IID, which simply means they are independent and identically distributed. And moreover, we assume that the expectation for each random variable exists, and we call it mu. And now we can just consider the average we get from these random variables. It's 1 over n times the sum that goes from k is equal to 1 to n. And as in the last videos, we denote that by x over line with index n. So and now the law of large numbers tells us that this new random variable converges to mu. And what this convergence means for the weak law of large numbers we have already discussed in part 28. And in this video today we will discuss a stronger notion of convergence for random variables. And this will also lead us to the stronger version for the law of large numbers. But first, let's recall what the weak law already told us. Namely, if we put a sample omega into the random variable, then it's unlikely that this is far off from mu. So more precisely, having this absolute value greater or equal than epsilon is low in probability for large n. So mathematically, this means that we measure the set for all omegas which satisfy this inequality with respect to the probability measure. Indeed, exactly this is what we call convergence in probability. So let's put this into a correct formula. So we have a subset in the sample space omega, and we measure that with the probability measure p. And as I've already said, we have the property that this difference here in the absolute value is larger or equal than epsilon. And now the statement is that this is a small probability for large n, namely it goes to 0 if n goes to infinity. And moreover, the claim is that this works no matter which small epsilon greater than 0 we choose. And indeed, we can visualize that in a picture. What we actually calculate here is the probability at the far ends. So if we cut here with the epsilon here and there, then the probability outside gets smaller and smaller if we increase n. So this is a nice statement, but it does not tell us anything about the point-wise convergence of the random variable here. However, this is definitely something we want to have if we think of a repeated random experiment. So more precisely, it would be nice if x over line n of omega converges to mu. And in the setting here you see this is just an ordinary limit in the real numbers. However, now the problem is the weak law of large numbers cannot tell us what happens at a given point here, because it can only say something about the whole collection of omegas in capital Omega. Therefore, you could imagine that actually strange things could happen for this sequence when n increases. So for example, let's say here we have the timeline in n, and on the y-axis we find the values of x over line. This means in this picture here, the sample omega is fixed. Moreover, let's say our epsilon interval around the mean is found here. This means the probability of lying outside of this stripe here should get smaller and smaller if n increases. And now if we ignore that n is a discrete number, we could definitely have a picture like that. This means we could always have points in time where our average is off more than our epsilon interval. The only thing we can say that at a given point in time we don't have it for a big amount of samples omega. However, this also allows that at other points in time other samples could be off very much as well. In other words, the weak law of large numbers does not tell us how many of our samples have a bad behavior. However, this is definitely something we want to know in examples where we actually calculate this average. In fact, the good thing is that the strong law of large numbers now tells us that almost none of the samples have a bad behavior. So you see, now we are ready for the formulation of the strong law of large numbers. And maybe a surprising fact is that we can use exactly the same assumptions as we have it for the weak law. This means we take infinitely many random variables and we call them xk. And there the important assumption is that they are IID, so the family is independent and all the random variables are identically distributed. And moreover, we also assume that the random variables are integrable, so the expectation of the absolute value of each of them is finite. Indeed, I should tell you it's possible to change the requirements here, so then we get another formulation for the strong law of large numbers. Nevertheless, I want to stick with this formulation here because it's the most common and practical one. But if needed, we will also discuss other formulations later. But first, let's write down the claim of the strong law. It just tells us that the average here, evaluated at a given sample omega, converges to mu. So this is exactly what we wanted to have from before. We have the pointwise convergence. And we get this property almost for all lowercase omega in the sample space omega. Indeed, we say that we have this nice property almost surely. So one can say this convergence here works with probability 1. So this means we can measure the omegas with the good behavior with respect to the probability measure p. Hence, we consider the set of omegas where we have this convergence here. And exactly this set has probability measure 1. So this is exactly what we mean when we say that something happens almost surely for omega in omega. So in other words, it definitely could happen that we have a lowercase omega where we don't have the convergence when n goes to infinity, but these omegas form a null set. So the probability of that happening is exactly 0. So please remember that the strong law of large numbers makes a claim about the pointwise convergence of random variables. And for the reasons you see here, this convergence is called almost sure convergence. And indeed, it's not so hard to show that this convergence is stronger than the convergence in probability. So you should remember that if we have random variables that converge almost surely, then they also converge in probability. And exactly for this reason, the strong law of large numbers implies the weak law of large numbers. In other words, if you have proven the strong law of large numbers, you also have proven the weak law of large numbers. However, in this video I will not write down a proof for this nice theorem here, because we will need some more time for that. But still here you should not forget that under these assumptions we have chosen, we always have the strong law and the weak law of large numbers together. Therefore, you might ask, why do we distinguish them in the first place? And the reason for that is that you could formulate the whole law of large numbers with different assumptions, and then it could happen that you only have the weak law of large numbers, but not the strong law. So it just depends which situation you consider, but if we take IID random variables, we don't have a problem, because then we have everything that we discussed now. In particular, if the expectation exists, then we always have the strong law of large numbers. And now you know that this one is very important, because it actually tells us what happens for large n with the averages of the random variables. Okay, then I would say we should continue in this direction, and we should talk about limit theorems in the next videos. So I really hope I meet you there, and have a nice day. Bye bye.